Hello and welcome to Down to Earth with Terry Virch, where we talk about what matters down here on planet Earth. Today we're going to talk about things that matter out in outer space. But if you love the podcast, please subscribe and give us a rating. And today we're lucky to have Katie Mack back on the podcast. She was one of my first guests last year. Dr. Katie Mack is a professor at North Carolina State University. She's an astrophysicist and also author of the new book, The End of Everything, that talks about how the universe will end. So it's the feel-good book of the summer, I guess. And she's also a pilot. Katie, thanks for coming back on.
Thanks for having me. I'm always happy to talk to you, Terry.
What's that telescope in the background? It looks pretty cool.
So it's a hand-me-down. So a friend of mine from Australia was leaving town and didn't want to take his telescope with him. And so I got to keep it. And it's just, it's a very, very basic telescope, little reflector, and it barely works. There's a lot of it that doesn't work. You know, the finder scope doesn't work. You have to kind of hold it with your hand and aim it at the star or planet or whatever. But you know, I can look at the moons of Jupiter. I can look at Saturn. It's enough, and it's nice to have, you know, just in case I need that little bit of personal cosmic awe.
Yeah, that's cool. Well, it's good background for your podcast interviews.
That's also true.
Well, so the reason I want to talk today is the James Webb Space Telescope is up in space, and there's lots of other bad news to talk about: Russia invading Ukraine and China messing with Taiwan and inflation and blah, blah, blah. We have lots of bad news. So what Webb is doing is really cool. And this podcast won't drop for a few weeks, but so far, knock on all the wood that we can, the deployment has gone amazing. And that was a really, really complicated, and a lot of guys were missing a lot of sleep, I think.
Yeah, no, it's been awesome to see how well it worked. I mean, this was an extraordinarily complicated engineering feat. The telescope is so big that it couldn't fit inside the rocket. They had to fold up the telescope to fit it inside the rocket. And so that
meant the rocket's big.
The rocket's huge, yeah. And so that meant they had to get it out into space and then unfold everything, you know, unfold the telescope, the mirror itself, unfold this giant tennis court size sun shield made of 5 different layers of sort of reflective foil. I mean, it was a huge thing. And then they had to, once they unfolded everything and got everything in place, they had to adjust all of these different mirror segments to be pointing properly. And they did it. And a lot of us were very, very nervous that something would go wrong, because this is an extraordinarily expensive instrument and it's going to be doing so much for us. And we were all very worried, but it seems to have gone perfectly. The engineers really did a great job.
I had John Grunsfeld on a few weeks ago. He's an astronaut who repaired Hubble a few times. He was the deputy administrator after my last space flight. And I had a chance to visit Goddard, which is where I grew up. My parents worked there. And when I saw Webb, I was like, wow, this is impressive. And as soon as I walked out of the building, I called John. I was like, dude, do you know how complicated this thing is? And he was like, yes, Terry, we're very familiar with that. So yeah, I was worried, and they pulled it off, which is amazing.
It is amazing.
It took years and billions of extra dollars than we had hoped to spend, but I think it's going to be worth the wait. Yeah. Give us a size too of how big it is. You mentioned tennis court. Why do you need the sun shield, and how big is the mirror?
Yeah. So the mirror is, I think it's something like tens of meters, like 18 meters, something like that.
Yeah, 16 or 8. Yeah, something.
Yeah,
like that.
I'd have to check the numbers. It's the mirror is huge, but the sun shield is even bigger. It's the size of a tennis court, and the reason it's so big is because this is an infrared telescope, so it needs to see very low energy light. So you know, the electromagnetic spectrum, the spectrum of light, goes from, you know, gamma rays at the high end to radio waves at the low end, and somewhere in the middle is visible, and then just the lower energy than visible is infrared. And in order to pick up infrared light, you need your detector to be really, really cold, because anything that's warm is emitting infrared light. People are emitting infrared light. That's why you can see people with infrared cameras. And so they needed to they needed to make sure that this thing stayed really, really cold. And when you're out in space and there's a star nearby shining on you, it's going to warm you up. So they had to make this giant shield to put between the sun and the telescope to stop that
Right.
that light, to keep the instrument from warming up. And that's also why they put it in the orbit they did, so that the sun and the earth and the moon are all behind that shield, and so that the telescope can be protected from all of that heat, and stay cold enough to actually pick up the infrared light that it needs to pick up.
And by cold, you
Yeah.
mean?
I mean, very cold. So
I think 40 Kelvin. I've seen that number.
Yeah. So yeah, something like that. The number I saw was negative 233 Celsius.
Yeah. Well, 40
so
Kelvin
40
is.
Kelvin.
Yeah. That's right.
So that's it's very cold. It's not much above kind of absolute zero.
Right.
In terms of, it's you need it to be that low, just so that it can actually get a signal and not be totally drowned out by its own radiation from just glowing with that infrared light.
Right. Infrared. So like I have a fireplace in my house, and when you stand next to it, you feel hot. That's infrared radiation, right? That's that's what the telescope is seeing.
Yeah. Anytime you're near something that's where you can feel the heat, if it's not the air bringing that warmth to you. So if you felt a warm breeze or something, that's not infrared.
Right.
That's the air itself being warm. But yeah, like if you're near a fireplace and you feel that heat, or if you put your hand near an incandescent light bulb and you feel that warmth, that's infrared light coming through there. By the way, I just checked, the mirrors are 6.5 meters.
6.5 meters.
Yeah, the primary mirror, the giant mirror for the telescope.
So that's almost a first down, to put, since we're using sports analogies. It's
Sure.
It's like, third and long is how big the mirror is.
Yeah.
So this amazing infrared telescope, and Hubble was visible. So Hubble looked at things that you can see. This is doing infrared, and that's what I really want to talk about today. Why infrared? Well,
so there are a couple of reasons why you want to look with infrared, depending on what you're looking at. One of the most important reasons is if you're trying to see things from the very early universe, from the very distant universe, which means from the very early universe, because it takes time for light to travel from that distant thing to you. And so at farther away you look, farther back in time you're looking, you need to go to infrared wavelengths to see those distant things. And the reason for that is that as the light is traveling from, let's say, some very distant galaxy, as the light is traveling to us from that very distant galaxy, it's traveling through a universe that's expanding, and the light gets stretched out. And that's called a redshift. And so very distant galaxies look redder than nearby ones, because that light's been stretched out by the expansion of the universe. And when you go to galaxies that are, so the first ones that formed in the universe, those galaxies are so far away that their light is stretched so much that they're not even visible in optical frequencies at all, in visible light at all. They're only visible in the infrared. And so if you really want to look at those galaxies, you need a telescope that can see infrared light.
Wow.
So that's one of the big reasons that you want infrared, an infrared telescope up there. And there are other things that are useful about infrared light. If you want to look through a cloud of gas and dust where stars are being born, for example, a dusty nebula, then you can use infrared light to look through these nebulae and see the stars being born inside nebulae. And you can use it to—
Just a second. Can we talk about that? Well, first of all, it's amazing. It's essentially a time machine in some ways.
Oh yeah.
It's absolutely. Looking at things that it's looking back billions of years in time.
Yeah. And
that's amazing.
And farther than the Hubble Space Telescope. So the Hubble could see, some very early galaxies. It could look back, more than 13 billion years, and the universe is only 13.8 billion years old, right? So looking back more, like I think it could look back maybe 13.3 billion years or something like that. James Webb Space Telescope will be able to look back, I think they said 13.5 billion years. So really, the first few hundred million years of the universe is going to be able to see. And that means that it'll be able to see some of the first galaxies that ever formed in the cosmos. And, we haven't seen those before. So we're going to learn a lot about how galaxies first started in the universe,
Right.
how the first stars and galaxies formed. It's going to be pretty amazing.
Is it kind of like people, your first 10 years, you change a huge amount. And the next 10 years you change. And then in 10 years after that, you don't change much. Is that the way the universe is? There was a
Um,
lot of change then in the early
yeah, I
part?
mean, there certainly was a lot of change there. The first galaxies were born in a universe that's very different than it is now. It was a much denser universe. We have reason to believe that the first galaxies had different shapes. They were sort of more compact than the galaxies we see today, maybe interacting with each other more often because everything was kind of closer packed in. And the space around those first galaxies was different in the sense that, like right now, if you go out into space between galaxies, there's not much there, but there's some gas, there's some hydrogen gas. And today, all that hydrogen gas is ionized, which means that hydrogen is usually a proton and an electron bound together. In ionized gas, that just means that the proton and electron are separate from each other. And it means that certain kinds of light can pass through ionized gas more easily. When the first galaxies were formed, the gas around them was neutral gas, and that was sort of more opaque to certain kinds of light than ionized gas, and so that changed the way that light moved through the universe. And as we're studying those early galaxies, we can learn about how that transition happened from a neutral universe to an ionized universe. And so we're hoping that by studying some of those first galaxies, we're going to learn something about how the starlight in the universe changed the gas between galaxies, how it changed the sort of the nature of all of the gas in the universe.
I didn't know that. If a hydrogen atom absorbs light, that's going to warm it up, wouldn't it? So does that mean it was warmer? Interstellar space was warmer than now?
Well, definitely interstellar space was warmer back then. Yeah. The space has been expanding and cooling since the beginning. So in that sense, it was warmer. But also, when there's more dense gas around, it kind of shields galaxies from each other. The light gets kind of trapped a little more. So a lot of things are different about how light moves through the universe. But that process going from neutral hydrogen to ionized hydrogen, we call that reionization, and it's part of how we try and understand, the sort of whole history of the formation of stars and galaxies in the cosmos.
Wow. So you think Webb can see back to 13.5 billion, but there's still a few 100 million years before that. In order to see that, so you go from visible to infrared, but if you keep on going, you get to microwave and then radio, right? Is that the next?
Yeah, well, so we can definitely learn some things about the universe in those other frequencies too. With radio frequencies, there are currently experiments or observatories being built that will be able to see the gas itself, the neutral hydrogen gas itself that the first galaxies were formed out of. And those telescopes are going to tell us something about that reionization process also. And those can look back to potentially earlier than the James Webb Space Telescope and start to see, because they don't rely on having like a really bright source. They're really looking at that gas itself and looking at it at very, very early times.
Right.
So we have that happening. Some of those instruments are going to be online in the next few years.
Right.
And then we also have the light from the Big Bang itself, the cosmic microwave background,
right?
Which is that we see that as microwave light. So what that is if you have a microwave telescope, you can actually see the light from the time when the whole universe was so early that the universe was hot and glowing and just on fire. So there was a time, at the very beginning of the universe was hot and dense and just sort of glowing plasma, and then it expanded and cooled. And as it expanded and cooled, gas and stars and galaxies formed. But in the very beginning, it was hot and dense and just fiery, this sort of, inferno.
It was just energy. Yeah.
Yeah. And the cosmic microwave background light is the glow from that early universe. So we can actually see that too with cosmic microwave background light. So microwave telescopes can show us before stars formed, before even neutral gas formed at all, when the universe was really in the final throes of the Big Bang. we can see that as well with microwave telescopes.
We talked about that when you're on the podcast. Wasn't there a woman astronomer that like, I remember the first person that ever saw the Big Bang, like how we talked about how incredible that would be. There were some scientists at Bell. They were doing like radio work, and anyway.
Yeah, there were a few people who were kind of the first people to see that microwave light without necessarily knowing what it was first. So there were these two guys, Penzias and Wilson, who had this microwave receiver, and they saw this like static in their receiver. They didn't know what it was. It was coming from every direction in the sky. They couldn't get rid of it, and eventually, by sort of studying that and talking to some colleagues who were thinking about the fact that you should be able to see the glow of the early universe, they realized that that's what they were seeing. They were actually seeing the Big Bang, that's
so cool.
That's kind of an amazing moment to think like, oh, I just saw the Big Bang in my
I just
telescope.
saw creation.
Yeah,
exactly. It's amazing.
Yeah.
So we, in theory, you could look back farther in time with microscope or microwave and radio telescopes, but when you do that, when the frequency gets longer, the resolution gets worse, right? So like an optical camera sees a really nice picture, an infrared, it's like 4K, and an infrared is kind of standard def, not exactly, but and then when you get to radio waves, it's like a crayon picture or something. It's a lot less.
Well, it depends on the size of your mirror, really.
The size matter, right?
Yeah. So if you have a really large mirror, then you can get good resolution. And so there's a relationship between the size of the mirror, the wavelength of the light, and the resolution of the instrument. So, for example, these radio telescopes I was talking about that are trying to see that early hydrogen light. Those are generally interferometers, which means that you get a whole bunch of dishes, and you kind of put the signals together from all these hundreds of dishes potentially, and you use that as sort of one big dish to be able to get detail. That's also how they did the Event Horizon telescope. So this telescope that saw the supermassive black hole in the galaxy M87.
M87,
yeah. So they made a picture of the light from that supermassive black hole, from things falling into the black hole basically, and that the reason they were able to see that, because that would be tiny from here, is so far away and not very big in space. The reason they were able to do that is they took radio telescopes from all over the world and put the signals together from across like the whole planet, and they were able to see that resolution. So it really depends on what the telescope is doing, and how big the telescope is, and how you're putting the data together.
Right. There's one in Arecibo, Puerto Rico, I think. It just crashed. It just fell.
Yeah.
It was so old, but that was so. Hubble is the size of a desk. Webb is the size of a first down. That one in Arecibo was the size of a football field. I mean, it was like huge. And then the really big ones. Okay, so you can get good resolution. You just need to make massive telescopes, and a little bit impractical.
I mean, and it depends on how far away you're looking, what kind of detail you're going to see, and all of that.
Right. Yeah. So with back to Webb, it's looking at early galaxies, which is going to be really, imagine seeing a galaxy for the first time. That's going to be, and we're going to have that sometime in the next few years. That's going to.
Yeah, I think the first data is going to come back around 6 months from now, and then we'll start to be able to, look at stuff. I have friends who have time on James Webb Space Telescope already. Cool. Like they've put in proposals, and they're going to be able to observe their favorite objects, or do surveys or whatever. So it should be really exciting.
So tell, as a scientist, you're a working astronomer, PhD. Telescope time, how does that work? Like getting time on Webb is a pretty big deal. You get street cred if you have time on Hubble or Webb, right?
Sure. I mean, technically anybody can apply for time on these telescopes. If you wanted to apply if you had an idea of what you wanted to look at and wanted to apply for time on the James Webb Space Telescope, you could. Probably wouldn't be very likely to get it without having the experience,
credentials,
But the way it works is that you write a proposal. So you there'll be a schedule on the website or whatever. It'll say that proposals are due on a certain date, and you will write down here's what I want to look at. Here's why I think it'll be interesting. Here's what it'll tell us. If we see it, here's how I'm going to analyze the data. Here are some predictions of, exactly what that data will show me and how it'll apply to this important problem. Here's some graphs of, if I see this, that'll tell me this. If I see this, that'll tell me that.
Right.
And then, you package that all up and you send it in, and a panel of other astronomers will get together and look through all the proposals and see which ones they think are the most, the criteria are usually things like, something that'll be really important, that'll give us some really important information about the universe, solve some important problem, something that's timely, this is a good reason to do it now, this is a good reason to do it with this telescope rather than something on the ground, for example, why do we have to do it in space? Why not, use some telescope on the ground? And then, there will be also some consideration of, do I think that this person is actually capable of doing that, like analyzing that data, doing that calculation.
Right.
Yeah. So that'll be another criterion for judging the proposals, and it's a competition, and the chance of your proposal being successful depends on how many people are applying. So I imagine if you apply for James Webb Space Telescope time, your chance is not great, but we put in proposals for, I don't put in proposals for telescope time because I'm a theorist, but I've put in plenty of proposals for funding. And I used to be on a panel for supercomputer time where we're trying to see who gets to use the supercomputer to do their calculations, and there are a lot of these shared resources among astronomers and physicists that we have to divide up, and usually it's through some kind of proposal process where you just make your case, and then we try and decide what's the best use of that resource.
The one thing, there's a lot of things I love about science, but one of the things I love about science is the peer review process. I know that's not fun and brutal, but it keeps things, it keeps everybody focused, and it keeps things truthful, and you know what I mean? You can't have crazy ideas. Well, actually having crazy ideas is good. All the best scientific discoveries were crazy, but at the time, but they required data, I guess is what I'm saying. And this may be the biggest problem facing the world, is the lack of truth that's out there.
But I think the nice thing about the way that we judge, science proposals in any direction, is that, and a lot of people don't understand exactly how this works. But what we're trying to figure out is, is this going to tell me something useful? Are we sure that this is going to result in the answer to some question? And so it's fine to propose, like, I think that the answer to, I think that this is the way that galaxies work, or I think that this is what dark matter is made of, or whatever. You can propose that. And as long as you can back it up with, and this is how I will answer that question, this is how I will show yes or no, then that's great. As long as it's a testable hypothesis that is interesting and feasible and fits into, some pictures. So we want it to be interesting. But there's this kind of there's this misconception that we're trying, that we suppress radical ideas, or that we just want to keep the status quo. You don't get funding to just do the same thing over and over again. Every funding decision, every observation decision, telescope time, computer time, whatever, novelty is part of it. It has to be telling us something new that we didn't know before. And so just confirming, yes, everybody was right the first time, and I'm not figuring out anything new about that, you'll never get funded to do that. so it is constantly, checking things. You might get funding to observe the same kind of phenomenon in a different way to show if that was right or not. For example, there was a recent radio telescope result that appeared to get a really shocking result about how early galaxies formed out of this neutral gas in the early universe. And a lot of people don't really know what to do with that result, because it doesn't seem to fit with our previous understanding of how galaxies formed and that process. And so there are a bunch of other experiments, other telescopes trying to observe the same thing to confirm or rule out the first one. So
right.
There's a lot of double checking, and if we see something surprising, we try and confirm it or rule it out. But we're not just trying to say, we're not all just lining up to say, yes, that is how it is. Like the progress is in constantly testing and checking and seeing
exactly
the edges of validity. And I think that's a very useful process to go through.
Exactly. Scientists test the hypothesis. You can say there's aliens, but now you have to bring the data to prove it.
Right.
And I think too often in the pop culture, somebody says something and it's like, that sounds right. It must have been this, or it must have been that. And then there's kind of a mob motion to not get vaccinated or whatever. And it, if we took more scientific method in our society, that would help things out a lot. So that's I want to talk about that a little bit.
Yeah, I mean, I think what the key thing there is, they say that when you're debating with somebody, a really useful question to see if they're debating in good faith is to say, well, what is it that would convince you otherwise, right? What data that could come to light to show you that this thing is not true that you believe? And if the person is not debating in good faith, they're like, well, nothing could ever convince me,
right?
But it's important to note that if you're proposing to do scientific research or something, or if you're presenting something in a paper, you do have to say, and here's how it could be disproved. That is really important as a part of it. You propose your hypothesis, and then you say, and this is how we test it, this is how it could be ruled out. And if you don't include that, if you don't include a way to falsify it, then people will say, well, this isn't really science, and you won't get
then it's ideology, not science.
Yeah. And so it's and people have debates about certain areas of science because they are hard to falsify or test.
Right.
And and there are ways in which you can make arguments about, well, if this is something that's mathematically consistent and fits in some bigger picture and so on and so forth, then you can kind of go along with it for a while. But eventually somebody's going to be like, okay, well, how do I rule this out or not? How do I prove it or falsify it? And you really, that step is really important. And when you're putting together a new idea or writing a paper, doing a calculation, going through yourself different ways like this could be wrong is super important, because somebody's going to bring it up. Somebody's going to ask you, what could show this wrong? Could show this that this is wrong, or how does this compare to this other thing? And you're always checking, and you're always looking for evidence for or against.
I love that quote you just had, like, what would convince you otherwise?
Mm-hmm.
That's a great question to ask others. It's also a good question to ask yourself.
Oh yeah.
If you, whatever issue it is, if you just hate those other people because they're evil and nothing could convince you otherwise, then maybe you're wrong. Like I've had some pretty serious soul searching and different things in recent years. And sometimes it's good to reevaluate and change your thoughts and positions. And that's what scientists hopefully are good at. Like I've used this example before, but Einstein was convinced that the universe was static. It wasn't.
Yeah.
And I think he said at the end of his life, that was the biggest mistake of his life, was thinking the universe was static, because it's clearly not. So, but he was willing to, he's like, I was wrong, and this is the way it is. So we all need that ability to say, I was wrong about that, or reevaluate things. So looking back in time, seeing early galaxies, but you also talked about seeing stars being born. And let's talk about that. I saw a visual infrared pillars of creation picture. It was a really cool example of what Webb can do for us.
Yeah. So if you have so stars are generally born in nebulae. So a nebula is a word for like a big clump of gas and dust in space. Right. And so those are places where stars are born, where there's a concentration of gas and dust, and that stuff comes together through its own gravity and forms stars and planets and things. And gas and dust tends to be pretty opaque to visible light, but infrared light can often pass through that, and radio light can as well. And so if you are trying to really investigate the interiors of those kinds of structures to see those processes more closely, then infrared is good for that. And as you say, you can see some really amazing things comparing a visible picture of a nebula to an infrared picture.
So nebula are actually graveyards of stars too, right? So it's a graveyard and a birthplace.
Yeah. So you can have different kinds of nebulae.
Right.
So you can have places where stars are born, and then it turns out that if you have a lot of stars forming, then some of those are going to be stars that have very short lives, and then those die as well. And so you can have these supernovae and remnants of supernovae. So when a star dies, and depending on the mass of the star, it can die in several different ways. But if it goes supernova, that can create a clump of or sort of, I don't know, the remains of the star get sort of exploded, and you can get a clump of gas that's from the star being blown up. And then there are other processes that can happen where if a star like our sun, when it gets to the end of its life, when it finishes all the hydrogen in the sun, what it's going to do is it's not going to blow up, it's not going to explode. What it's going to do is it'll sort of blow off the outer layers of the sun, and then the core will collapse into a white dwarf star, which is kind of sort of dense stellar remnant. But when it blows off the outer layers, that's going to create this nebula of gas sort of outside that white dwarf. And that's often called a planetary nebula. It doesn't really have anything to do with planets,
Right.
But that's a kind of sort of stellar.
But it's like it's a sphere. It looks like
it's like it's like a little bubble.
Right.
So the reason they're called planetary nebula, I think, is that when they were first discovered, they were sort of little discs in the sky.
Right.
And so are planets, and so people used to call them that.
Right. So how long do nebula last? Like, they're not around for billions of years, are they?
Well, it depends. I mean, it sort of depends on what's going on in the nebula. I think that stellar remnants can last hundreds of millions of years at least, but I think some of them can last billions. It depends on what's going on.
Oh, really? Okay.
And then the things that are forming stars, it depends on how quickly it goes through the stars. But I mean, I think I would think somewhere around tens or hundreds of millions at least for some of these things. I'm not really sure.
Right.
They change as different processes are happening in them, or like things move through the universe.
So our sun was not born at the beginning of time. There was a galaxy, it died and exploded. And are we the children or the grandchildren or the great grandchildren? Do you know?
So our sun is about 4.5 billion years old, or 4 or 5 billion, maybe about 5 billion years old.
Right.
So there have been a few. I think that there have been maybe 2 or 3 generations of stars before our sun. I don't know exactly the number, but but it's more than one. I think it's more than 2, maybe like 3, maybe 4.
So we may be great grandchildren of
something like that. Yeah. So the way you can tell is that the first stars would have formed out of just hydrogen and helium gas, because there wasn't anything else.
Right.
And then those stars formed a bunch of other elements. And then when they exploded, they spread those elements into the gas that formed the next star, and so on.
So say that again. What you just said is amazing. So today we have, there's carbon, and there's metals, and there's all kinds of stuff. Yeah. There wasn't in the beginning.
No. So in the beginning, there was hydrogen and helium and a little bit of, I think like a little bit of beryllium or something, lithium, little bit of lithium. So there were just a few elements at the very beginning. Those were elements that were formed in that hot Big Bang, in that, sort of hot gas that was glowing. So at some point, the universe was so hot that nuclear reactions were happening inside just space itself, just generally.
Oh, wow. Interstellar space was a nuclear bomb.
Yeah, wow. Exactly. So a few elements were formed during that process. That's called Big Bang Nucleosynthesis. So a few elements were formed then, but it was mostly hydrogen and helium, almost entirely hydrogen and helium, a little tiny bit of lithium, and trace amounts, a couple other things. Right. And then, the gas cooled, and you had just a bunch of cool hydrogen, a little bit of helium gas, and then the first star formed, and the first star formed from that pristine gas, and then the star fuses hydrogen in the core and creates higher elements as it goes through its life, and as it goes supernova and so on. And so it pollutes the gas around it. This is the term we use. So it pollutes or enriches the gas around it. And so then that makes the rest of the gas be mostly hydrogen, but a little bit of these higher elements, carbon and oxygen, and some metals. And then the next star is formed out of that slightly enriched gas. And so each generation has higher, what we call metallicity, so higher amount of like iron and other heavy elements. And so we can look at our sun and say, okay, based on the number, the amount of metal in our sun, there have to have been a certain number of generations before our sun. I think it's
planets too, right?
And well, yeah. So I mean, planets are all, well, except for the gas giants, like they're mostly heavier element. I mean, in terms of the solid things, they're mostly heavier elements. So the gas giants are mostly hydrogen, but they have some heavier elements in the cores. And then the rest of the terrestrial planets are heavier elements. So you can't really make planets out of hydrogen, just hydrogen.
Right.
So it takes a few generations to get, lots of rocky planets.
So I wonder if early stars even had planets.
I mean, the first stars couldn't have, because there just wasn't anything to build them out of.
Though they could have Jupiters, though. Will Webb be able to see that?
Yeah, well, no. I mean, Webb won't be able to see individual planets that far back. But Webb will see some really interesting things about planets around other stars.
Right. That's a totally different subject, but this is.
Yeah, and that gets into this thing about aliens that you mentioned.
Exactly. Well, real quick, looking back in time, Webb will only be able to see galaxies. It won't be able to see individual stars, do you think?
Not for the very, very distant stuff, no.
Not for the early stuff.
Yeah.
But the galaxies will tell us something about what Okay.
Yeah. So we'll learn something about what the population of stars were in those galaxies by looking at the images.
That's so cool. So let's talk about other planets that we see. Because of if a planet goes in front of a star, it gets a little bit dimmer, so you can see that. You can see the wobble. The planet pulls on the star, and the star pulls on the planet, and it wobbles a little bit from gravity. But what will be different when Webb looks at those?
So, so there are a few different ways to find planets around other stars. We call those planets exoplanets or extrasolar planets. What Webb will do is Webb will be able to see depending on, I won't see all of them, but it'll be able to see some of those planets individually and learn something about their atmospheres. So what it's going to be able to do is analyze the chemistry of the atmospheres of planets around other stars. And that's really important, because if we look at the atmosphere of a planet around another star and we see that the atmosphere is just a bunch of hydrogen or just a bunch of like carbon dioxide or something like that, we're like, okay, that's a sort of normal planetary atmosphere. But if we see a whole lot of oxygen, if we see a whole lot of water, if we see a whole lot of stuff that would not sort of persist forever just based on like geophysical chemistry, if we see stuff that's volatile that we think is mostly formed through biological processes, then that'll give us a hint that maybe there's life there. And so there are certain markers for like chemical markers, things that are out of equilibrium, where it has to be constantly created by a life form. And we can look for those chemical signatures. And if we see out of equilibrium chemistry, if we see chemistry that doesn't look like it could just be, from volcanoes or plate tectonics or something, some kind of chemistry that really would need a life form to create those quantities of gas, then that's a clue that planet has life. And the JWST will be able to actually, analyze the chemistry of the atmospheres of planets around other stars in a way we've never been able to do before. And so most likely, the first real evidence for alien life will come from something like that. So it's probably not going to be, picking up a tiny skeleton on Mars or something. It's probably not going to be a spaceship crashing into Earth. Probably what it's going to be is we're going to get the spectrum of the atmosphere of a planet around another star, and we're going to see weird chemistry, and we're going to say, oh, that is indicative of life.
Right. So I need to rephrase it for the fighter pilot who level of discussion. Something like oxygen is very reactive. The scientists call it volatile. Oxygen tends to make rocks rust or whatever. It just doesn't hang around forever. So unless you have trees creating oxygen, there's probably not oxygen would not stay in a planet. Okay. And Webb will look at the planet, but it's not gonna be able to test the oxygen. I think it's going to use a spectrograph using this, use the star. Talk about that. For fighter pilots, how does that work?
So for and I should put a disclaimer, I'm not an expert in exoplanets or planetary chemistry, atmospheric chemistry. I don't know for sure if oxygen is one of these markers. I think it's one of these markers, but like there are other kind of chemical markers. But the way we figure out the chemistry of something in space is we look at the spectrum of light. And so if you have certain chemical elements or molecules in a gas and you pass light through that gas, those substances can absorb light at only certain frequencies and emit light at only certain frequencies. So that's why, so for example, neon lights have a particular color. It's because when you excite those atoms, they emit light at the same frequency, and so that gives it a sort of uniform color. And with a cloud of gas, depending on what the gases are, they will absorb light at particular frequencies, and it relates to how the atoms or molecules are kind of moving around with respect to each other, how you can sort of move electrons up and down energy levels and stuff like that. But the point is that there are certain specific wavelengths where light is absorbed or emitted.
So can I ask a question?
Yeah.
The wildfires in Colorado and California, you see these really red atmospheres. So is that sort of an example of a spectrograph where the dust is blocking certain colors of light and letting the red light through?
So that's a slightly different thing because that's a scattering thing. So that has to do with how the light is scattered and redirected by the dust. But there's a specific sort of signature to if you were looking through. I don't know of an example in everyday life where we have this happen, but
well, the chemicals change the light, and the chemicals you can analyze the light you're getting, the infrared light, and
and so
what chemicals are there.
Yeah, and so you can see, you can spread out the light like in a prism, and you'll see that certain colors, there's a little bit of light missing at certain colors. So you get these dark lines at certain colors, and that'll tell you that something that absorbs light at those frequencies exists in that atmosphere. And so if it's the frequency that is associated with water or oxygen or some complex molecule or whatever, then that tells you that chemical is there. And so I mean, you can find online a spectrum of the sun, where it's you can see this, like, it's a long sort of tape of a sort of rainbow of different colors, and there are all these little dark lines in it, and all those little dark lines are different chemicals, different elements in the sun that are absorbing, or in the sun's atmosphere, that are absorbing a little bit of light. And so that's how we can tell what chemicals are in the atmosphere of the sun, and we can do that with other stars, and we can do that occasionally with planets around other stars, and the James Webb Space Telescope is going to be able to do that. And
it has a spectrograph. Yeah. So those are called absorption lines, right?
Yeah, absorption lines.
So recently we have a neighbor that's a lot like Earth, Venus, and some scientists think they might have found a chemical marker there of a chemical that only exists due to life. Do you remember that? Like last year or two ago? Yeah.
So that was a really interesting, sort of saga where there was this chemical that was something that we didn't expect to find through, we didn't expect it to be produced in sort of geological processes. And a bunch of astronomers said, look, we looked at Venus, we saw this, a high abundance of this chemical. Maybe there's life in the clouds of Venus.
Right.
And it got really complicated because then some other groups said, actually, we looked at the data, we don't see that chemical at all. And then it's also like, well, do we really know that chemical was formed by life? Could it have been formed by some kind of geological process? And I don't actually know kind of what the final word on that is. I think that the detection of the chemical at all has been called into question, and so I think that we're kind of back to the drawing board on that. But it was a really interesting time because yeah, that's how we would find aliens, is that we would see that weird chemical imbalance, and we'd argue about it for months and months, and
like
everybody
years
would,
and years, probably.
yeah, and everybody would try and say, well, but maybe it could be formed by, you know, a geyser of some kind, or maybe, you know, maybe you've got some contamination in your you know, spectrum or whatever, and it's going to be a complicated technical back and forth. It's not going to be, you know, something comes out of the sky and says, hi, here I am.
It's not gonna be little green men, right?
No.
Well, I think the shotgun answer, not shotgun, but the default position, I think, for most scientists is it's not aliens. And so you're going to need a lot of proof to get to that threshold. Yeah.
I mean, aliens, it always has to be the last hypothesis, right? Because there's just
there's a lot of
extraordinary,
other,
you know, extraordinary claims, extraordinary evidence, that kind of thing.
Right. That was that Richard Feynman?
I think it predates him, but
it's just everybody. Yeah.
But it, you know, the crucial thing, though, I think, is that it's not that we don't think aliens exist, right? If you talk to astronomers, almost all of us are pretty sure there are aliens out there in some way. They might be, you know, the alien equivalent of a slime mold on a rock around some, you know, volcano planet. Like, I mean, it's not necessarily, they're not necessarily like people flying around in spaceships.
Right.
But the idea that life only exists on Earth is really, I think most of us would consider that to be an extraordinarily unlikely hypothesis. And so, you know, so we do take seriously things like looking for the signs of life on other planets, because we're pretty sure there's something out there, and we think that this is how we'll find it. Why
don't we look at planets in visible light and do spectroscopy with visible light? Like, why haven't we done this before? Why is Webb the first one to be able to do this, or the best one?
I mean, we can do spectroscopy with visible light. We have taken spectra of atmospheres around other planets. Just James Webb Space Telescope is just going to be better at it. It's got a bigger mirror. It's got this great spectrograph instrument. Like, it's going to be able to do better and see more things than previous instruments. So that's my understanding.
Is infrared better than visible at that kind of thing?
For that?
Planetary spectroscopy?
I don't know.
Yeah, I don't know.
That's beyond my my expertise there.
Okay. It's a pretty cool thing. Do you know how, I mean, again, you're not the James Webb scientist. I certainly am not, but you understand all the basics here. So is, like, how far away are these planets? Like 10 light years, 100 light years?
So the kinds of planets that we know about, the exoplanets that we found are not that far. So I mean, I would guess between tens and hundreds of light years, but I don't think we can go further than that for a planet. 1
light year is incredibly, unfathomably far away.
Yes.
And the nearest star is like almost 3 or 4 light years away.
It's 4.2, I think.
Yeah, there you go. So like, these distances are just unbelievable. I don't know what the analogy is, but I'm sure it's, you know, looking at a penny in Beijing or something is
I don't know. I mean, but yeah, the big problem with looking at exoplanets is not necessarily just that they're far, but that they're sitting right next to a much, much brighter object, which is their star. Right. And so disentangling the image of an exoplanet from the image of its star, that's the hard thing. That's the really difficult thing.
And it has to be orbiting like this, right? If it's orbiting like this, we won't get the spectrograph.
Well, so it depends on what you're actually trying to observe. If you want to directly image a planet separate from a star, then it needs to be orbiting face on, so that it has a distance from the star, or it could be, I mean, you could catch it at the right times if it's orbiting the same plane, but you know, you want it to be far, which means it's going to be a far out planet, probably not like an Earth-like planet. It's going to be something out in the outer solar system. If you want to find it through the transit method, it has to cross the face of the star in order to give you that transit, to block out a little bit of the light of the star. And if you wanted to find it through that gravitational tugging, where it's wobbling the star back and forth, then it's better if it's orbiting in the, you know, perpendicular, like orbiting the plane.
face on,
crossing in front of the star. Yeah.
right.
So it depends on how you're looking for the planet, where it's best to see it.
Do you think if the aliens are looking at us, would they see markers in our atmosphere?
I mean, if they could analyze our atmospheres, for sure. But depends on what kind of instruments they have.
Right. If they've got the James Webb Space Telescope or not.
Yeah.
They probably named it something else.
Probably.
So what's going on? Are there any other interesting capabilities? We got really far back in time, looking at new stars and planetary atmospheres. Anything else that Webb is exciting people?
Well, with these kinds of projects, it's always the unexpected stuff that's going to be interesting and surprising, right? So we're going to see, there are a few things that we know to look for, right? We know to look for these early galaxies. We know to look for stuff around other planets. But we're going to get, better and deeper information than we have before. So maybe we'll see something really surprising. Maybe we'll be able to get really great images of something we never expected to see before.
Right.
So I'm excited about, what we don't know about yet, what we haven't thought of yet. So maybe
Right.
there'll be something really cool that'll come out of, we'll be looking for something in a nebula and we'll see something we never expected, or we'll be looking for early galaxies and we'll see some kind of new stellar process that we didn't know about, or whatever. Right. I think I'm excited about all of that.
That's super cool. Well, so I don't know if it's your main area of interest, but it's the subject of your book is what's not the past, but the future.
Yeah.
And all the different ways we're all going to die,
Yeah.
heat death, and that I forgot what it was called, the exploding at the speed of light.
The big rip.
The big rip. Yeah. So that was just really cool talking to you about that. Is Webb going to enlighten any of that research, like what the future might have in store?
Well, I mean, what it'll do is it'll tell us a lot about early galaxies, which then gives us some information about the evolution of the universe, and that can be useful for extrapolating into the future. So in all of astronomy, we're only looking at the past. We can't look at the future, but we can directly see the past. And so what we're always trying to do is take that information and extend it to the future, extrapolate into the future, and figure out, what might happen next. So this, so it's not that it's not going to really answer those questions completely, but it'll give us new hints about the distant future, because it'll tell us a lot more about the distant past.
Mm-hmm. I wonder what, like, black hole research is always important for physicists and astronomers, right?
Mm-hmm.
And is that going to tell us stuff about black holes?
I'm not sure. I mean, usually when we see black holes, we see them with really high energy radiation, X-rays, and things like that, because what black holes do is they create this gravitational field where matter sort of spirals in, and as it's spiraling in, it heats up, and you get these accretion disks that are glowing in X-ray light. So black holes, usually it's like gamma ray X-ray telescopes that tell us a lot about black holes. But
if those are redshifted enough, could you ever redshift a gamma ray burst into infrared? I wonder. I don't know.
I don't know how far. I think gamma ray bursts stay gamma ray bursts even in the very distant universe. But I don't know how far into into other frequencies they can get. I'd have to check that.
That would be a big redshift.
Yeah. I mean, they could get to X-ray for sure. I think there are, there's X-ray. There's some aspect of gamma ray bursts that give you X-rays, but I don't know. I don't think they can get all the way down to.
No, I mean, not from the event itself. I'm talking about from the speed of the universe. If the speed.
Yeah.
Well, I mean, that fast.
Yeah, I mean, I guess if you had a gamma ray burst super early in the universe, but it would be. I'm not sure if you can get the stars that make gamma ray bursts in the very, very, very early.
That early.
Like that. Yeah. And I don't know if it would be bright enough to see more than a few billion light years away. So
right. Anyway, it's super cool. I'm looking forward to the next 5 or 10 or 20 years. I don't think Hubble's lasted a long time, but it also got serviced. But
yeah, Hubble has had
Webb is not going to get serviced. Yeah.
No, it's way too far away for anyone to go visit it. So that's another reason we've all been very nervous about the deployment of Webb, because we knew that if something went wrong, if some gear got stuck and the mirror couldn't line up, like there's nothing you can do.
Right. There's no shuttle rescue mission coming.
No.
So, well, thankfully it worked. And
Yeah.
So as far as the title of your book, where are you at? How's the universe going to end? There, you gave us a couple of options.
Yeah. So, I mean, most likely it seems like the universe will end in what we call the heat death. So that's where the universe it's expanding, it's cooling, it's emptying out. Everything is kind of fading away, and stars are dying, and everything gets cold and dark and empty. And that leads to this ultimate heat death where everything is over. So that's the most likely end of the universe. It's not necessarily the most exciting or dramatic. But it does, it takes a really long time for that process to carry through. So that's good, I guess.
Yeah, it's going to be a while. Are our brains going to suddenly reappear from quantum mechanics in the future? Do you think? In
Well,
this podcast?
That's a question for. That's something that comes up in the book. The idea that quantum fluctuations or statistical fluctuations in the universe could create sort of little blips of intelligence here and there.
Right.
I mean, the thing is, a lot of weird things can happen when you have sort of an infinite amount of time, and just the laws of physics. So, we'll see.
Quantum mechanics plus infinite time is interesting. Well,
Yeah.
Hopefully I'll see you before then, but if not, maybe I'll see you like a trillion years from now.
Yeah.
We're like, what happened to everything? Why is it all black?
Yeah. Well, yeah, hopefully we'll be able to go flying sometime.
Yes, that would be much better.
Since I became a pilot, I still haven't had a chance to take you up in an airplane.
You-
I'm sure it would be the most thrilling thing you've ever done.
No, it'll be awesome. I haven't flown for a long time. So
Yeah.
my neighbor's got a Cub. He's been asking me to go, and I'm always busy anyway. So I need to go. I'll take you up on that.
Excellent.
Well, thanks for coming on, Katie. I know you're busy, but this is just cool stuff, and it's fun to talk astronomy, and I can't wait to see what the web guys. Congrats to the guys at Goddard so far, so good, and hopefully that keeps up.
Yeah, thanks.
Thank you. And if you love the podcast, don't forget to subscribe and give us a rating. We'll see you next week. All right.
Okay.
Stop